Let's start with a quick review of lecture 11, and then we'll go on to our current lecture, which is essentially going to complete, hopefully complete the operating systems section. And then time permitting, we will hopefully go on to the next major topic, which is data structures. All right. So in the last lecture, we looked at the simple machine cycle, where we looked at without pipelining and with pipelining, and we looked at various issues that came up with pipelining. And we looked at two specific examples. One in which the amount of time taken for different parts of the instruction were different. And the second issue was that of data dependency. And we saw how both of these issues could be addressed. Of course, this is just some of the issues. There are more issues that could happen, but this is, of course, an overview course. So a lot of the details will be expected to be covered in the individual courses that are going to be covered in the next 7 semesters that you hear at IBA. Then we went on to operating systems, and we talked about user interface versus kernel, the difference in functionality. We looked at the booting process, and we looked at what batch processing was during the early days. Let me make sure people are muted. And we went on from there and looked at the issues without operating systems and what were some of the advantages of the operating system. And one of those specifically was having the different hardwares that could be used to be separated from the application developers. So the operating system would actually worry about the different types of hardware interfaces that one could have, and this was done using device drivers. Another important thing that operating systems did as the hardware became faster and faster was that they allowed what was referred to as multitasking. And we talked about multitasking, how that operates using the term context switching. And we saw some of the issues as to how context switching can be achieved. And basically, we looked at when a context is switched, we essentially said that some of the key registers, such as the basic registers you have over here, and the PC and the IR are, of course, saved, because that is critical to tell you where exactly where exactly is the next program, the next instruction going to be executed from the location in memory, and what value does it have. But I mentioned that the memory itself is generally not swapped. Okay. And we ended the last lecture by saying we'll discuss as to why the memory itself is not swapped. And let's take a closer look at that today. So here's another example, and this is from your book, figure 3.6. It refers to it as multi-programming, but I will not differentiate between multi-programming and multitasking. Essentially is slightly different versions of the same thing. The way this is shown in the book is that you have two programs running. So you have process A and process B. You might call it processes or programs. And there are different time slices, which we referred to earlier on. Okay, so I referred to these time slices over here. These are again referred to over here. And you notice a special term over here, which is called the interrupt. Okay. Now the question is that when one task is supposed to finish executing and another task is supposed to begin, how does the CPU actually know when to stop? Because the CPU, as you can imagine, has a series of instructions, and it's simply going ahead, loading one instruction after the other. And this is in practice achieved by something referred to as an interrupt. Interrupt is basically a hardware level signal, and you can think of it as an external signal coming in from some external hardware. It could be, for example, a clock signal. You could have a clock an external clock, something you can imagine just like a physical clock. Internally, internally you could have a clock which after, let's say, every so many milliseconds, it generates a signal, okay? And that signal could be called an interrupt. And once that interrupt is generated, um, once that interrupt is generated, the CPU basically knows that it has to switch, okay? So it's going to switch, start the process of context switching, and then it will switch to another process, okay? So that's all I'm going to talk about in terms of interrupt. It's a fairly lengthy concept, which will be discussed in more detail in one of your probably your microprocessor course later on. And there are things like interrupt handlers and so on as to how you can achieve the switching. But let me just, so all you need to know as far as this course is concerned is what is an interrupt, and it's an external piece of signal, okay? Now, the next topic within operating systems is something called virtual memory and paging, okay? And this sort of links in to this issue over here that I mentioned, that memory is generally not swapped, okay? So let's try to understand why memory is not swapped. Now, the issue basically is that a lot of times your physical memory, which is your RAM, of course, could be limited, okay? And your actual program could be a lot larger. So here's a simplistic example where your physical memory, let's say, is 32K only, and you need to load a program which is very large. For example, it's 64 kilobytes, okay? You can replace kilobytes with megabytes or even gigabytes in actual practice today, but the concept is more important over here. So here you have the physical memory, okay? So this can be referred to as your physical memory. And here is something called a virtual memory, okay? So we're going to refer to this as your virtual memory. So if you want to load a program which is larger than your physical memory, essentially what you have is a mapping, okay? And you will define something called a virtual memory. And in the virtual memory, you can go as large as you want. You can make it 64K or 128K, or essentially there is no practical limit to how much you could go. Of course, it does depend on the addressing space that you have. Okay, so if it's a 32-byte computer versus 64-bit computer, then the address space of the virtual memory is also limited. So here's an example. Let's say that your actual program is 64K, so it's going from 0 to 4K over here, and their contents are, let's say, something, a block of code called A. Then from 4K to 8K, you have another block of code B, and so on. Okay, so you have a whole bunch of block of codes. Now, if you want, if you don't have enough physical space, what you can do is you can put half of your program or half of your data on the actual RAM, or some portion of it on the RAM, which is fast, and some portion of it which is not fitting in your RAM onto a slower medium, such as your hard disk. Okay, so if you think about the analogy, this is sort of like saying that you have a limited amount of space. Suppose going back to the analogy that you do in your homework assignment, right? And you, in Introduction to Computing, you've been asked to, refer to a whole bunch of books. So suppose you have 10 books, but you only have space on your desk to accommodate, let's say, five books, right? So you bring those 5 books onto your computer, onto your desk, and you start referring to it simultaneously. Okay, and you're reading one page from here, another page from another book, and so on. The difficult assignment, more difficult than I normally give. Okay. Now, unfortunately, your space on your desk only has 5 books, space of 5 books. So what you do is the rest of the books you're actually putting on your shelf. Okay, so your hard disk is sort of like your shelf space. Now, obviously, to be able to access your shelf space or your filing cabinet, will be slower. You will have to get up from your chair and go and access it. So it'll be much slower. But the amount of space over there is hopefully a lot larger than you have on your desk. Okay. So this could be only 32 kilobytes versus on the hard disk, you may actually have a gigabyte of space. So there is no, essentially, there is no limit as to how much space you can have over here. But this is a lot faster. As you can imagine, your desk space, it's a lot easier to access stuff on your desk. But it is limited. So it's fast, but limited, and this is slow, but unlimited. Now, the question is, what happens when you need to refer to the sixth book? Okay, and you're referring to the first five books. Now, all of a sudden, you need to refer to the sixth book. Now, you may think about, well, I don't have space for the sixth book. So what I can do is I can take one of those books which I haven't been referring to for a while, and I'll put that back on the shelf, and I'll put the sixth book on my desk. Okay, so this is something called swapping. Okay, or paging as well. So think of each one of those books as a page of memory. Okay, here I've referred to a page as 4 kilobytes. So each one of these chunks of code is 4 kilobyte long. And what we're doing is essentially taking stuff from the shelf and putting it onto your desk, so to speak, or taking it from the hard disk and putting it into your RAM. And anything which hasn't been used for a while, you could have a fancy algorithm to figure out which book or which page was the most hasn't been used the longest. And what you simply do is swap that into your hard disk, and you bring your page which you need into your RAM. Okay, so this basically is the concept of paging. Okay, the two concepts are intertwined. So paging basically means that you're taking stuff between your RAM and your hard disk, and you're swapping these. And the virtual memory essentially helps you in that, because in virtual memory, you can have a map. You can say that, well, the contents, let's say the block of code A is in location, is on the physical memory location, is, let's say, at location 20, okay? And B is on the physical RAM, it's at 24, and C is on 28, and so on. And some of these things which are not on the actual RAM could be in different locations. Okay, so this could be, let's say, at location 0.5 gigabyte. Okay, and so on. So I hope that is clear. So here is another example. So in this case, basically what I'm showing you is that this doesn't have to be contiguous. So you can see that A, for example, is at 16K, okay, block of code A. B, on the other hand, could be at a different location. Now, can somebody tell me why is it possible that B is not in the same contiguous space in the RAM? Why do you think this could be possible? And why is it possible that C could be before B? I'm having a hard time hearing whoever speaking. Ji Musab. Ji Musab, go ahead.
So perhaps C was loaded first because we used it first, and next we loaded B in.
Okay, so it's possible that B was loaded first, and then C was loaded, but then B was swapped. Okay, so B wasn't being used, and you needed something else. Let's say you needed D, so you swapped B out, and then sometime later you needed it again. Okay, so when you wanted it again, it was put into a different portion in the physical RAM. So you understand that each one of these pages could actually be in a completely different location in the RAM. Okay, and after a while, this could all be completely jumbled up. But in the virtual memory, you need to be able to figure out where exactly is it on the in the physical RAM or on the hard disk. So you need to have some kind of a pointer over here. Okay, so this location is sort of like a pointer. Okay, it's saying that, well, this is on the RAM and it's at location 16K. Okay, this guy here may say that it's on the hard disk and it's at location 104K. Okay, So this could be in general thought of as the concept of a pointer. So I hope, I guess you haven't really touched upon the concept of pointer in your introduction in your other introduction to programming course, which you should hopefully be taking simultaneously, but that will probably be taught towards the end of that course. But pointer can be simply thought of as another address. Okay, so so in the contents itself could be another address. So this is another address, and this address over here is referring to 28K. So if you understand that, now let me ask you, how much space would you need to store this value over here, the pointer itself? And do people understand the concept of, it's a very important concept, the concept of pointers. And so it's important to understand it the first time around. Can somebody tell me how much space would you need to store this address? Would it be 1 byte, 2 bytes, 4 bytes, 8 bytes, whatever?
Sir, Shayan here.
Ji Shayan.
Sir, it would depend on the type of processor, if it's 32-bit or 64-bit.
Yeah, exactly. So if it's a 64-bit computer, then clearly the addressing has to be 64-bit. So it will take 64-bit over here. If it's 32 bits, then it'll have to take 32 bits. Okay. So this is just a quick revision question.
And
Jinanda.
so what's virtual memory?
Okay, so virtual memory can be thought of as simply a map. Okay, so it's a space in your actual memory. Okay, so here's the actual memory. At the beginning somewhere, you have a map. Okay, and this map is simply, it doesn't have the actual contents. Remember, now notice that this size over here is 4 bytes, but the actual content over here is 4 kilobytes. Okay, so in other words, the map itself will be a fraction of the actual size of the contents. So in order to have this entire map in memory, how much space would this virtual memory map take? Can somebody answer that? So this is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. I think that's 16. Okay, you have 16 blocks. So how much memory would the map itself, the virtual memory map, take?
Sir, 64K.
Okay, so you're reading that from over here. The map itself, does anybody disagree or agree with that?
It would take 64 bytes. 64 bytes.
64 bytes. How did you calculate 64 bytes?
It's 4 bytes per each.
Right. So the actual map is going to take 64 bytes, not 64 kilobytes, but simply 64 bytes. Why? Because, and don't get confused by the starting address over here. This is the starting address of the actual block A. Okay, but the map itself is actually going to only take 64 bytes because this map will say, well, block A is located at a particular address, and the address would be given by these 4 bytes. B would be given by the next 4 bytes. C would be given by next 4 bytes. Now there's a little bit of a trick over here. Now the hard disk space could be a lot bigger. Okay, so the actual size could differ because you also need to specify whether it's on the RAM or on the hard disk. So let's say that it takes 8 bytes. Okay, you take 4 bytes to specify the actual address and another 4 bytes to specify the location. So the location could be either in RAM or the location could be in hard disk. Okay, But I'll come up with another example of this just in case some of you are confused. But let's go on. Okay, so hopefully we'll look at some other examples and you'll get a better understanding. So essentially what we've said is that, yeah, is there a question? Okay, so essentially what we've said is that when physical memory is limited, you might want to use virtual memory and paging, okay? And virtual memory overcomes this issue. Pages that are not in use are put on the hard disk. This was, as I explained, that anything that you're not using for a while, you can simply swap it onto the hard disk, okay? And active pages are loaded in RAM as needed, okay? So this is sort of like another level of abstraction. If you remember the concept of abstraction, basically what we're saying is that instead of directly addressing your memory, you're going to first use a map to be able to get to the actual location, okay? So here's another example. This is an example of multiple programs with virtual memory, okay? So suppose that you have program A and you have program B. Now the virtual memory can start in both cases from address 0. Okay, so this is the virtual memory address. So it's basically saying that the block of code A is at location 0 in the virtual memory address. Block of code B is, each one of these is 4 kilobytes long. The actual length of the code, here's A. And B is another 4 kilobyte piece of code. C is another 4 kilobyte piece of code, or it could be data as well. So this is the virtual memory address. Okay, so this is the VM address. Now, in order to get A, what are we going to do? I haven't shown you the actual location, but there's going to be a pointer which is going to point to where it's located in the actual physical memory. Okay, so when it needs to get to A, it's going to go to this particular location. All right, when it needs to go to B, it might go to this particular location. And when it needs to go to C, it might go to this particular location. Okay. Now, the second program could have the same addresses 0, 4, and 8K, and it has different pieces of code or data over here, X, Y, and Z. And these could, in the physical memory, be in different locations, but they won't obviously be overlapping. So for example, X could be in location 12K, okay? Y could be over here, Z could be over here, all right? So this is just a depiction of that. So hopefully now you understand that. Why is it that memory doesn't need to be swapped? Okay, so can somebody explain to me, by using virtual memories, why is it that the actual memory, when you do a context switch, why doesn't the memory actually have to, when you're going from program A and all of a sudden you stop running program A over here, so this is going back over here, so you're running program A over here, and now you switch to program B. And we said that you do need to copy your registers and your PC and IR, but you don't need to swap the actual memory. So can somebody try to explain why is it that we don't really need to swap the actual memory
Sir
when we're
Zohair.
going from A to B? Ji Zohair.
Sir, we don't need to swap the memory because we have already pointed where the data is stored in another in the physical memory. So when the data is used, it is stored in the accumulator only using the address.
Right. So essentially, you have the right idea. Let me just rephrase that. So basically, what we're saying is that the physical, when you swap between A and B, okay, now even though the addresses are the same, you might say, well, if the addresses are the same, it's going to use the actual same location. So we need to take all of this data and replace it with B, okay, with this data, A, B, C, because they're using the same location, they have to be swapped with X, Y, Z. Now, if you weren't using virtual memories, that would be the case. But since you're using virtual memories, the actual physical location of A, B, and C are different from X, Y, and Z. And as long as the virtual memory maps are there, you don't have to worry about actually swapping those. Is that clear?
Sir, I have a question.
Ji, Umar.
Yes, sir.
Sir, the operating system must swap a page if it needs to brought another one into the memory. So,
Yeah.
sir, if it swaps a page right before it is to be used, so the computer has to bring it again. So that would be a problem if several processes like this came into the CPU.
Absolutely. That's a very good point. What happens sometimes is that you have when you look for a page in memory, and this is different from what we were just talking about. So hopefully, the topic that I said is clear, that why you don't need to actually save the memory, simply because these two programs. The short answer is that these two programs are using their actual content is in different locations in the actual physical memory, and that's why that doesn't have to be swapped. Okay. Now, coming to the point that was raised by one of the gentlemen over here, that what happens if you're running a program? It's like saying I'm looking for book number 6, but book number 6 is not on my desk. Okay. Now that's called a page fault. All right. Page fault, which basically means that the page that you're looking for is not in memory. Okay. So as soon as you have a page fault, you're looking for something, it's not in the physical RAM, then what do? You actually go to the hard disk. Okay. So when you're going to access O and P, you're going to have a page fault. Why? Because these two are not in the physical memory. Now, what the gentleman said is that what if you continuously need to use all of these and then O and P also? Okay, so then you have this issue that you're continuously referring to data which is not on your physical RAM is so small that you're having page faults all the time. Okay, so that results in a lot of problems. That basically results in an extreme slowdown of your computer, because now you're having to access your hard disk every time you try to do something. Now, have any of you experienced this in actual practice on your computer? And when do you think you've experienced this? When you have too many
Sir,
page faults? Sorry, who is that? Ji Musab.
Musab,
Yeah.
would error 404 be classified as this?
No, so it doesn't result in an error. Okay, so all we're saying is that now you continuously swapping. Okay, the page fault is not an error. Okay, it simply means that what you're trying to access on your desk is not there, so you're going to go over and bring that book from your shelf and get it. It's not a problem, right? But it simply takes a lot longer time. So memory access could hard disk access could take hundreds and thousands of times longer time in terms of speed. Okay.
Sir, is it disk thrashing?
Sorry,
Sir, is it also known as disk thrashing?
disk thrashing. Yeah. Well, disk thrashing is, I think, slightly different. That's the disk thrashing happens when I might be wrong on that, but that happens when your hard disk is also your data on your hard disk is not in contiguous spaces. Okay, that's a slightly different topic. But
Sir, is it during boot up?
sorry,
System boot up? Is it during system boot up?
no. During system boot up, things are okay. But if you're sometimes, I hope none of all of you have got computers. Well, either you haven't used your computers so extensively, but sometimes, let's say you open up 20, 30 windows, browser windows. Okay, you're looking at 20, 30 browser windows. All right. Now, what happens? Things start to become slow down, right? Or if you're trying to do too many things on your computer simultaneously, so everything becomes slow down. Or if you're trying to copy something from one hard disk to another, and let's say you've got two USBs and you're copying, or you've got several USBs and you're trying to copy a lot of data from one to the other. Okay, so you might have noticed that your computer suddenly becomes extremely slow. Okay, it almost comes to a standstill because it's sort of facing something called a deadlock. Okay, in a deadlock situation, what you have is that you need to access some code of A, and in order to complete this instruction, you also need B, but B is on the hard disk, so you need to load B, but you don't have space for B, and so you swap out A, and so you continuously swapping in
Sir,
and swapping out data. G, Tariq.
like when you have a lot of programs running and you open another program, it's a long time for it to start.
Yeah. So, and most people at that point, if you go to an IT specialist, like one of your colleagues, hopefully, they will tell you you need to get more RAM. Okay, why is that? Because your current RAM is not sufficient to handle so many processes. And if you doing, for example, gaming, I mean, gaming takes up a lot of space. So if you're doing gaming and at the same time trying to do something else, then you will run into these kind of problems that you
Sir,
simply don't
but
have enough hard disk. Yeah.
we can also increase the speed using a solid state drive also.
Yeah,
SSD.
that's true. Very good. So what you could do is instead of simply increasing your RAM, what you could do is you could speed up your hard disk as well. Okay. So SSD, as being referred to over here, is solid state hard disk, which is a lot faster. Okay, sort of like a flash hard disk. So that the speed over there can become faster. But still, the speed of hard disk access versus RAM access is a huge difference between those two. Okay. So your better solution is to simply increase your RAM if you're running into those kind of problems.
Ran, boot loops
DRAM.
also are boot loops also connected to something like this?
Booting, did you say?
Yeah, when there's a boot loop issue, it just keeps never boots properly. It just keeps repeating itself.
I'm not sure if I understand your question. Basically, booting is a process when you restart your computer. Okay, so when you
Mm.
first turn it on.
No. Basically, there's something called a boot loop. It
Boot.
loops.
Okay.
It
Yeah.
keeps looping.
Yeah. So yeah, that could be that could be one of the problems that you could be having. Okay. So essentially, basically, what you're saying is the computer is going through a thrashing phase. It's trying to get data. It doesn't have enough RAM to support that data, and it's going between the hard disk and your RAM. Okay. So I hope that answered that
Sir,
question. Yeah.
I want to ask, for example, if we have two virtual memories like over here, is
Yeah.
it possible for both of them to possess the address 4K, or will there be any problem if like
No.
over here at 4K we
No.
have B, and we also have
No.
Y?
Yeah. So it won't be a problem because essentially when you want to access the address 4K, okay, it's going to tell you the location. Okay. So the map is going to tell you where it's actually located. So you will actually go to the address 28K to get the address 4K when you're running program A. When you're running program B, when you want to get the contents of address 4K, you're going to go through this pointer. It's going to tell you that it's somewhere, let's say, over here at 20K. So both of those are going to actually access different contents in the actual physical memory. Okay. So I hope I answered your question. Another question?
Yeah, sir, do we have individual virtual memory for each program that we have to run?
Can you say that again? I didn't quite hear you.
Do we have to have individual virtual memory for every program that we run?
Yes, yes. So you would normally have separate virtual memory for every process that you're running, okay? In order to be able to differentiate between the actual physical address of this particular program and the other program. Otherwise, then it defeats the purpose of that, okay? Okay, so let's move on. So this was some of the things that the operating system does. Okay, it manages memory, and when I said initially that there are different tasks that your operating system handles, one of the things that we mentioned was memory management. Okay, and paging and virtual memories. These are some of the two things that the kernel, essentially the kernel right at the center, at the lowest level of your operating system does, okay? The process management scheduler, as you've already seen, is basically what it's doing is it's scheduling different activities. So when task A finishes, you need to execute task B, and when B finishes, you need to execute task C, and so on. So a scheduler normally does this, and it doesn't have to be round robin. So for example, if task A or program A is, for example, printing something, it could be taking very long, and B and C are very fast. So it might actually execute B and C, back to back. And then when A has the printing is done, then it will go back to program A. So this is what something called a scheduler will manage. Okay. Device drivers and some of these other issues, I'm not really going to go into details, at least at present.
Sir,
G.
I want to ask one more thing.
Yeah.
When we have multiple virtual memories, when one is being used, where is the other stored? Does it also occupy some part of the RAM?
Yeah, so
itself?
the actual virtual memory will occupy some part of the actual RAM as well, okay? And the virtual memories hopefully don't take up too much space. So they may actually, the virtual memory itself may reside, so all of this may actually reside somewhere in the actual physical RAM, okay? So I haven't shown you the whole contents, but somewhere in the actual physical RAM, this is going to be there, and this is also going to be there, okay? And hopefully those won't be swapped out, and those will be considered, the operating system will make sure that critical things are not really swapped out, okay?
Sir Tariq,
Ji Tariq.
are we supposed to know how much space the virtual memory will be taking, and how are we supposed to know that?
Okay, so as I said, if the virtual memory is basically, well, I haven't given you a very precise answer to that, okay? But if I hypothetically give you in a homework assignment or something, and I tell you that, let's say that this particular, the actual pointer over here, which is telling you where it is located, is, as I said, 8 bytes long, okay? And and there are, let's say, 16 blocks inside your virtual memory. So then you should be able to calculate it, right? It's a simple calculation, 16 times 4, 16 times 8. Okay, hopefully that isn't too complex. All right.
So it's a combination of the address and the location.
It's a combination of the number of blocks that you've divided it up into. Okay, so here I've taken 4 kilobyte blocks. So the actual, so I'll give you a more, I'll give you maybe a homework assignment in which you can figure this out. Okay, but look at this particular example, and you can see that it depends on a few factors. It depends on how large your actual virtual memory space is. Okay, it depends on the size. So it depends on 3 things essentially. It depends on the size of each block, and then it depends on how much space you're using. All right. So hopefully,
sir.
yeah, hopefully you should be able to calculate that.
Sir, Sohaib Mughal.
Ji Zoeb.
Sir, by this method, if we create an software that opens infinite number of windows, so would we be able to crash someone's computer?
Yeah. You see what will happen if you start opening up an extremely large number of windows? Okay. Can somebody tell me exactly what would happen? So based on what I've just said, what do you think is going to happen? Can somebody try to answer that? What happens? So I've got 2 programs, A and B. What would happen if I opened up 20 programs or 20 browser windows?
Sir,
Ji Musa.
So the places in the RAM would fill up, and then we place the same error you were talking about earlier.
Yeah.
Where it's not there.
So basically, you can think of each one of them as a separate program. Okay. So your browser window one of these would be one program. Another browser window would be another program or another process. And the more the more you open them up, the more processes you're going to be executing. Okay, and each one of them would take up would have to have its own memory space, and eventually you'll end up doing a lot of hard disk swaps. Okay, and you would essentially crash. Uh, Eventually, you would have a situation where you get into a deadlock situation. Okay, a deadlock can be sort of explained if you think about a traffic signal. Okay, so you're going on a traffic signal, and in very simple terms, your car is going to try to go through this roundabout. It happens a lot in Karachi, of course, and everybody is trying to go around the roundabout. Okay, what happens when there is a lot of traffic? Okay, nobody gets through. Why? Because this guy is waiting for this guy is waiting for this guy, this guy is waiting for this guy, and everybody is waiting for everybody else. So at that point, you run into a deadlock and the system crashes, and that's when people get out and start shouting at each other. Or you have a police cop and comes in with and says, well, we have to turn the signals on, which will be a slightly different situation. Okay, so those are situations where you have deadlocks, and that's when the computer actually crashes. Okay, so moving on, now we've been talking about the hardware becoming faster and faster, and I'm looking at the operating system level, but at times when I'm talking about the operating system, I'm going to delve down to the hardware level. Okay, because the operating system is actually managing the hardware. So we've spoken about multitasking. Um, Operating systems also need to be able to manage something called multiprocessing. Now, can somebody try to explain what do you think is the difference between multitasking and multiprocessing? Multitasking
Sir,
you already got, right? Yeah, go ahead.
is handling the multiple processes at the same times, while multitasking is handling different multiple threads and program tasks, executing them at the same time.
Okay, very well put. So basically what we're saying is that in multitasking, you had a single processor. Okay, in multitasking, you had a single processor and you were trying to run multiple programs or multiple processes within that same CPU. Okay, a processor simply means a CPU. In multiprocessing, on the other hand, as hardware becomes faster and faster, it becomes denser and denser. So on the same motherboard, now you can fit multiple CPUs. Okay, and these CPUs are generally separate chips, and so they need to be connected by a bus, just like your main memory is separate from your CPU. So what you could have is multiple CPUs fitted onto your motherboard. Okay, so you have multiple processors in the same motherboard. And so you could have CPU 1, 2, 3, and 4, and so on. You could have 4 CPUs, 8 CPUs. Generally, it's a multiple of 2 or a power of 2. Okay. And so, what do you think could be an advantage of having multiprocessing or multiple processes?
Sir, speed.
Speed. So let's say that you wanted to do the simple calculation, for I is equal to 1 till n, and you want to do x is equal to x plus 1 or something ridiculous like that. Okay. Do you think that would help? That would become faster if you have multiple processors.
Sir, in multiprocessing, throughput will be its maximum. So the maximum efficiency could be achieved.
Okay, throughput could be maximum, but that's not really answering my question. So what I'm saying is you have for I in range 0 till 10 to power, 100, you're doing something ridiculous like that, and you're doing x is equal to x plus 1. Okay, it's a simple loop. It's going through the whole process. It's simply adding 1 to x. Now, if I ran this on a computer with a single processor versus one with 4 processors, you think there's going to be a difference in the speed at how long it took you to finish this program?
I don't think so.
Gee, Tariq, why not?
Because it's one program, right? So only one processor would be doing it.
Yeah. Yeah. So you're right, Tariq, that basically what you're saying is that this program will essentially be running on one of the processors. Okay, it'll either be run on this or on this and so on. So if
Yes.
that particular program is running on a particular processor, then the speed, the duration is going to be determined by the speed of this processor. Having additional processors is not going to help. G.
So I was saying that it could be that if one processor halts, the other processor could continue its work. The other processor's work.
If one processor halts, did you say halts?
Or yeah, or stop because of
Yeah.
an error or something.
Yeah. So, but we're looking at the simple situation where it's not because it stopped working or something. We're simply saying that this processor over here is there, and this is taking up the bulk of the speed. Okay, bulk of the time. So essentially, what we're saying is that having multiple processors may not always help you. Why is that? Because if your program is something which cannot be broken up into parallel programs, then it doesn't really help to have multiple processors. However, in most cases, what happens is that if you think about what your computer is doing, it's already doing a large number of processes. There's a clock running, there's the browser going on, there's a Zoom session going on at the background, you have your email. So already all of these processes are going to be occupied. But if one of these processes is like using 99% of your CPU time, then having all these other processes is not necessarily going to help you, because these processes are mostly idle. And it's only this process which is being, extremely hard driven. Okay. Unless you can write this program in such a way that it can be executed in parallel. Okay. It can be executed in parallel by a number of processes. Now that something like that is not at least not of immediate interest to us, but I thought I'd mention it in going. Okay. Parallel computing is sort of an advanced topic, and there's something called multi-threading and so on, but I'm not going to touch on that. And I'll leave that to if you have extra time at some point to discuss. So, but you understand the issues in multiprocessing. So you've understood multitasking versus multiprocessing. Now, another concept that comes in, and this is something that people referred to earlier as well. What's the difference between a single core versus a multi-core processor? Now we're talking about the hardware level again, but again, this is what the operating system has to manage. So what do you think is the difference between a single core versus a multi-core processor? Any thoughts? And would you call this a multi-core processor, or would you call this a single core processor?
Sir, it will be called a multi-core processor.
Okay, so this wouldn't be called a multi-core processor. Why? Let me explain why. So in a single core, the idea is basically that on a single chip, the processor has a single CPU, okay? On a multi-core processor, you can think of it as multiple CPUs inside the main CPU. All right, so it's basically the reason why all of this is happening is because now the hardware is becoming so compact and so dense that the old days where a single chip could only have a single processor is now replaced by a situation where you can actually have multiple CPUs. So you can think of this as each one of these as a small CPU, okay? And now things are getting a little bit more complex. Now you have the concept of caches, okay? I mentioned this earlier on as well, but let me give you a hierarchy of caches. Now, all of this is basically your RAM, okay? Broadly speaking, each one of these can be thought of as your random access memory. However, your main RAM is what's referred to as your main memory, okay? And that's what is normally shown as accesses separate chip being accessed through a different bus. Okay, being accessed through a bus. Okay. However, your caches are small pieces of memory which can actually be inside the same chip. So this is your main memory, but a smaller memory and much faster memory could actually be inside the same chip. So this is an individual chip. So this boundary is the boundary of a chip. Now inside that you could have memory as well, okay? And these are called caches. And there are different levels of caches. So in level 1 versus level 2 versus level 3. I haven't shown you level 3 in here over here, but you could conceptually also have level 3. So level 1 is the fastest, but it's also the smallest, because it's expensive. It's also the most expensive. Level 2 is slightly less fast, okay? It's also bigger and less expensive. Level 3 is even less faster, bigger, and even less expensive. And the main memory, as compared to the caches, is now slow. Of course, as compared to the hard disk, it's a lot faster. G, question.
Sir, what between these levels?
Can
That
you
means
repeat your
the
question?
first one. What are meant by level 1, level 2, and level 3?
Okay.
And
So,
what are
so that's exactly what I'm explaining. So level 1 cache is cache which is a small piece of memory. Okay, it could be, for example, 8K, 8 kilobytes. Okay, and it would be on inside the chip, and it would be made of special circuitry which is very fast. So not all RAMs are the same. Okay, not every car is a Ferrari or Maserati or a Porsche. Think of this as one of those fast cars, very expensive, and think of this as your station wagon, which is much bigger, can take up 8 people, but is much slower as well. Okay, so these are fast cars, these are slower cars, and fast cars generally are more compact. So this is a very simplistic analogy, but I hope you get the idea. So this is faster RAM, slower RAM, and generally these caches can be on the same chip. Okay, as compared to the main memory, which is a lot bigger. So this could be in terms of gigabytes. Okay, so this could be in terms of gigabytes. These are typically in the order of kilobytes, much smaller. Okay, similarly, as compared to the main memory, your hard disk again could be in terms of terabytes. Okay, so you can see 3 times bigger over here, 3 times bigger over here. So it's simply showing that your architecture is
sir.
fairly complex now. Yeah, question.
Yeah, Ryan, why can't we just connect multiple L1 caches to directly to the memory?
Okay, so so I'm not sure if I quite understand your question. Are you saying that instead of the L2 have simply L1? Is that your question? Or
No.
instead of the
It's
main memory
basically
have just a whole bunch of L1 caches?
yes. No. Basically like a whole bunch of L1 caches, but no L2 cache.
Okay.
It's just directly to main memory.
Yeah. So this is sort of like fine tuning, okay? Because there's a cost to everything, and L1 you can't, even if you have, let's say, a whole bunch of L1s, they would eventually take up probably more space than an L2 cache. All right. So so this is going into slightly deeper topics in your hardware, which would probably be addressed at a later stage in your courses. But basically, it's an issue of architecture. At some point, if you think about why is it that we have hard disks and main memory, okay? The question that you're asking is sort of similar to saying, instead of having a hard disk, why not have a lot of main memory? You understand that? You would need a lot more space to have a terabyte of main memory, and it would be a lot more expensive as well. So the same analogy carries on over here, that if you have a lot of L1 to make up for the L2, it would probably become a lot more expensive. Okay, besides other issues. Okay, so sometimes you need to be able to say, well, I'm going, something which I really need quickly, I'm going to keep in the L1 cache, which is expensive, but I can have a little bit of it. And then the stuff that I don't really need that often. Now, why do you think L2 is over here? Why is it that you don't have this scenario? Okay, why not L1 over here and L2 in here? Can somebody try to tell me why that wouldn't make sense?
Because L1 is smaller than L2.
Okay, but
You
what
can't
about
store
this?
enough.
What about the speed? Think about your core.
Sir, it should be nearer the cores.
Yeah, yeah. So it should be near the core because your fastest stuff, for example, your desk space, which is your right in front of you, you want to have that closest to your core. All right. So the core memory, once in a while, you need to access. So there's going to be paging between these as well, and there's going to be paging between these as well. So what you can't find in your cache, you're going to look in the L2 cache. What you can't find in the L1 cache, you're going to look in the L2 cache. What you can't find in the L2 cache, you're going to look in the main memory. What you can't find in the main memory, you're going to go into the hard disk. So that's sort of setting the hierarchical level. And because most of the time you're going to be looking in the first cache, this has to be the fastest. Okay, so you can't have a slower speed over here. You need to have the fastest right next to you. And when that faults, then you're going to go to the other one, which is slower and then slower and slowest. Okay, so
Sir, why are we using caches?
why are we using what?
I'm saying why are we using the caches? I mean, why can't we?
Why can't we use what else instead of cache? Sorry, there's too much echo in the auditorium. So I guess your question is, why are we using caches and why do we need to use cache in the first place, right? Is that your question? Why do we need to use caches in the first place? Is that the question? Anyway, I'll try to answer that. So basically what cache is doing is essentially what the original paging is doing earlier. So remember what was virtual memory doing? So virtual memory was basically saying that I don't want to keep everything in the hard disk because hard disk is slow. So I need to have something fast, and I'm going to use RAM. But since RAM is limited, there has to be some mechanism to have an overflow situation where stuff that is not available in the RAM can be put on the hard disk. Okay, so the same analogy goes on over here. When you have multi-core processors, then within the same CPU, what you can do is you can have fast memory, really fast memory, but a very small amount of it. And that can be used as your first level of, the first place you look for. So if you repeatedly, and in most of the time, you're actually using a small portion of the code. Okay, you're not looking. You don't. If you've got 1 GB of code, you're not going to be using all of that. You're going to be probably using a few kilobytes of that at any given time. So you want to keep all of that in your L1 cache. Okay, it's sort of like, the going back to the same analogy of books. It's like saying that if you're looking at 5 books at the same time trying to do introduction to computing homework assignment, then within a particular book, you're probably going to be referring to, let's say, 5 pages at any given time. So those 5 pages is something that you maybe want to tear away from your book. Don't do that. But let's say you tear it away and you put it right in front of you. Okay, so that's like your L1 cache. And then when you don't find those pages and you need to refer to the 7th or 8th page, then you go back to your book. Okay, and then when you need to refer to another book, you refer to maybe something on the shelf. Okay, so that's sort of the hierarchy that we're going, keeping stuff that we need to refer to very frequently in your fastest memory. When you don't find it over here, you go over here, and so on. Okay, sort of a hierarchy of of um, of of memory in terms of speed. So hopefully that answers some of the questions you have. And again, a multi-core is essentially saying that it's sort of like multi-processors, except that now within the same processor, you have multiple core. And today, if you buy a good computer, you can actually have, 4 processors or 8 cores or 16 core within the same CPU. And again, you can also have multiple CPUs as well. Okay, so take a look at your computer and you'll get an idea as to what you have. And if you've got a recent computer, you probably have a multi-core processor, multiple processors as well.
Sir, Zoeb Mughal here.
Ji, Zoeb.
Sir, but the multiple CPU versions are not available for the personal users, I guess. They are more likely for the servers or other things.
Not really. So for example, if I look at my own computer, I think I have a Core i7, and it's got a whole bunch of processors. So if you buy any decent laptop today, yes, a few years ago, you generally get a single core, a single processor. But today, if you buy any computer, an i7 or something, or better than that, then you will find multi-core processors. Okay, things are becoming cheaper and cheaper and faster. Yeah.
Sir, having more cores doesn't necessarily means more speed, right?
Yes. So as I said, if you have a highly parallel architecture, so in other words, you can actually get hundreds of cores in your computer. But if you have, let's say, a 100-core computer and your main function is simply to do something very linear and not very parallel, okay, all you're trying to do is do one thing, so that wouldn't really help. It's when you're doing a lot of things in parallel that multiple cores come in handy. Okay, I hope that concept is clear.
So basically, it depends upon the app. If
Yeah.
the app is optimized for multiple cores, so then the speed will be affected.
Exactly. So most of the gaming industry actually can use what is called GPUs. Okay, and those are highly parallel. So a lot of times when you, for example, working on a game, you're playing a game, then your computer is actually computing things which can be highly parallelized. Okay, I don't want to go into too much detail of that, but basically it requires a lot of computations, matrix computations, to be able to calculate your next image. Okay, so those can be done in parallel. And so so in gaming computers, you generally require a lot of cores. That definitely helps. Okay.
Sir, what about multiple multi-core processors?
Yeah, so same idea. So you could have multiple processors, and at the same time, each processor could be multi-core as well. Okay, the more the merrier, generally speaking, especially if you have applications which can utilize those parallel processing. Okay.
Sir, Zoeb Mughal.
Ji, sir.
Sir, for example, if we have but both are single core and a processor with 2 cores, so which one will be faster?
Okay, so those get into interesting questions. The question is, would a single processor with 2 cores be better, or 2 processors with single core each? Okay, I'm not 100% sure. I'm not a hardware expert, but my guess is that a single processor with dual core would probably be better. Okay, but I could be wrong on that. And you could try to search for that, and you'll probably get different answers. In fact, when you try to do advanced computing and things like deep learning in advanced AI courses, these things become very important. Your architecture becomes very important, and then it also depends on the kind of application you're running again. Okay, so I don't want to give you a generic answer, because again, all of this will depend on what kind of processes are you running. Okay, so each type of processes could require a different architecture.
Thanks.
Okay, so here's an example of a multi-core. It's got 2 processors, and each one of them have got a dual core. Okay, so you've got core 0, core 1, core 0, 1, so on. Or you could say there are 4 cores, 2 processes. There's something called multi-threading, but let me just skip that. Okay, so the topics that we've covered so far in this course are, and let's just take a quick look. We've looked at algorithms. We started off by looking at algorithms. We looked at flowcharts and complexities. And then we sort of jumped to the hardware level, okay? We went all the way from transistors, logic gates, digital circuits, microchips, and to computer architecture, okay? And then we also looked at machine code. So this is all the software level. Everything above this is the software level. We looked at machine code. We've looked at operating systems. We've looked at the user interface, which can be thought of at a high level of abstraction, and the kernel, which is lower level. So now what we're going to do is we're going to go back to the application development. We also looked at programming language. We looked at Python to some extent. The next major topic that we're going to now focus on is called data structures, okay? And this is, as you can see, it's now going a little bit at the high level. So not going all the way up till the algorithms level, but data structures is essentially slightly below the programming level, okay? So let's talk about data structures. We've got about 5-10 minutes, so let's just start the topic. So can somebody explain to me what do you understand, somebody who maybe has taken this similar courses before, what do you understand from the concept of data structures? What does the term data structure imply? And why do you think it could be?
Sad here.
Yes, sir.
Would it be implying the way data is stored? We talked about how data is stored in the memory, but how it is organized in the memory.
Exactly.
And how application program would access it.
Exactly. So basically, data structures is essentially is how do you organize the data in a computer, and more importantly, how to make sure that the data is stored in memory effectively. Okay, so you could have two ways of storing the same data, but one could be a lot more efficient versus another. Okay, and basically, there are different data types. So we've already seen some of these, and they'll be categorized into primitives versus non-primitives. But let me just first talk about primitives. Primitive simply means, as the term itself explains, it's the simplest version, okay? So we've seen integers so far. In Python, we've seen float, we've seen Boolean, we've seen string, right? I hope that you remember that from some of our earlier discussion when we were looking at the Python programs. Non-primitives are something which are more complex, okay? And arrays, lists, we've seen lists as well in Python, something called sets and dictionaries. If we get a time, we'll take a look at those. Those are more complex data types, okay? All of these are essentially what are referred to as data types. So let's take a look at some simple examples. So for example, if you're using Python and we say a is equal to 3, okay? Now, for example, if a is a 1-byte integer, so since 3 is an integer, let's assume that it is being stored as a single byte in memory. So I'm going to show it as follows. I'm going to show it as a label, which is basically the name of the variable that we're looking at. So a is the variable. Now I'm going to say, go show you the address, and I'm going to show you this in decimal as to where it's actually stored and the actual content. So when you assign the variable a is equal to 3, clearly the contents are going to be 3. This is going to be 1 byte long. So the address is basically going to be 1 byte long. Okay, so it's going to start off at 100 and end at 100. Okay, so 1 byte integer. What's the maximum value of that integer, by the way? 2 to the power?
32 minus 1.
2 to the power 32, 2 to the power 32 minus 1. 1 byte. Does somebody disagree with this?
Sure.
Zoe Mughal here.
Can it be 2 to the power 7 minus 1?
Yeah, something like that. Okay.
255.
So it's basically going to be something like 2 to the power 8. Okay, because you can have 2 to the power, you have 8 bits, and each one of them can be 0 or 1. So roughly it's about 2 to the power 8. Okay. I'm
Sir,
not
Zoe
going
Mughal.
G.
Sir, if we are talking about integers, then wouldn't it be 2 to the power 8 and after computing that will minus 1 because it's
Yeah.
like that.
Yeah, but I'm not going to the details of it because you can have negative numbers and positive numbers, but roughly this is not going to be a very big number, okay? It's only going to occupy 1 byte. Now let's take a slightly more complex example. So let's say that you have a is equal to 3, and now it's being stored as 4 bytes. So the largest number is approximately 2 to the power 32. Now remember, you can calculate this very simply as 2 to the power 30 times 2 to the power 2. This comes out as 4 to the power 30 is 10 to the power 3 to the power of 3. Okay, but anyways, it's just for reference purposes. So now tell me what would be the contents and what would be the location in memory of this. So if this is 4 bytes, how much space in actual memory would it take? So starting with, let's assume that it's located at location 100. So the content would be, let's say, the number 3. And clearly this would go from 100 to any guesses?
199, I guess.
199. Remember, each one of these addresses is 1 byte. So when you say 100, it means, so let's say if you say 100, it means a 1 byte location. Okay. And the next address would be 101, 102, and each one of them would be 1 byte long. Okay. So that's how I'm showing it. So
Then it would be 103 then.
So
No,
103.
104.
Yeah. So
4
it would
bytes.
go up till 103. So it would be 4 bytes long, and it would take 4 bytes in memory over here. Okay. Now think of b is equal to 3.0, and now this is a floating point number. In Python, actually, it takes a ridiculous amount of space. Let's not get into why it does that, but it takes 24 bytes for a floating point number. So where do you think, how much space is this going to take? Again, the number over here is going to be 3.0, but how much space is this going to take? From 200 till?
224.
200 and?
92.
292. Not sure where the 92s are coming in from. This is all in decimal, so don't worry about hexadecimal. So if it's 24 bytes long, it's going to go from 200 till
224.
223 actually, because it's starting from 200. Okay, it's going to go up to 223. Similarly, this went up to 103, not 104, because it's starting at 0. Now now suppose that you have c is equal to true. Now this is in Python. This takes actually a lot longer, but let's assume that it takes 1 byte. Okay, how much space should actually a Boolean value take? So you want to have either c is equal to true or false. Okay, so if you wanted to take the minimum amount of space to store this, how much space do you think it can take?
Shouldn't be 1 bit.
Exactly. So it can actually be stored as a single bit. However, in Python, this will take a ridiculous amount of memory. But let's assume that because it's hard to work at the bit level, and a lot of times memory space is not very it's not very critical. So what happens is that almost out of time, so I'm going to stop soon. But what happens is that you actually end up taking slightly larger. So let's assume that you take 1 byte. So C is simply going to start at, let's say, 300, and it's going to end over here. Okay, and the value over here is going to be true. So in the next class, we'll go on to looking at slightly more complex data types, starting with strings, and then we'll go on to non-primitives as well, and see how these data types are actually organized in memory.